let's just go through the few things. So, thanks a lot for those who have submitted the assignments. Obviously, we haven't marked them yet, but it will be over next 2 weeks, and then you will get the results. Um, yeah, so let's just do the announcements first. So the second assignment is coming, right? It will be online from today's midnight, and there will be instructions. We will go through the instructions in the practicals. And again, this assignment is 25%. It's due in the end of week 10 or 24th of September 2021 at 8 p.m. And again, if you need an extension, drop me an extension request or an email first to discuss it if you want to. Again, I strongly recommend to start the to start working on the assignment as early as possible, because again, this is the second assignment where it becomes a little bit probably denser, because essentially the end of the assignment is the week number 10, which is the week before the last week of the trimester. And then you don't have much time. You have other um, assignments, you have exams and so on. And essentially the delay to start the assignment leads to effectively to accumulation of those problems, and I really don't want you to go into those, because it's unpleasant and stressful. So I really do recommend you to start as early as possible, and and work on it in a normal, non-panicky, just good, right way. There is one more thing to tell. So the quiz number 2 will be announced next week, right? And will be available in week 9. So today is our week 7 started, and it's a terrible Monday. Right, so the quiz will be available in week 9. Essentially, this is because we need the material which I am telling you over the next 3 weeks to complete this quiz successfully. Well, as successfully as you have completed the quiz number 1. Yeah. So just to reiterate what is going on, the assignment, the second assignment, will be available starting from tonight. I'll just check it once again, and we'll release it according to the schedule. Quiz will be in week number 9, so it's a little bit probably early to talk about it. Anyway. Last week, we had sort of a beautiful lecture and nice and simple lecture. This week, we will have a material which is less nice, less pretty, and definitely less beautiful. But what it does is it expands the applicability of the linear models to a really, really wide range of data. What we will be talking about is the exponential family of distributions and GLM. GLM is for generalized linear models. So you already guess from the names that what will happen effectively is we will provide a mathematical mechanism to generate a family of distributions for which some sort of a linear model will apply, and we will call it generalized linear model. Again, in R, everything is pretty much simple because everything is already written, the libraries have already been created, and everything is already fine. So you can just take the data set, put it in, provide the explanatory variables, and create the model and fit the model and look at the results. So that's how it works in R, but it's always nice and helpful to understand what happens behind that library, right? And behind those few seconds of time which R takes to fit the model. Yeah. So again, last week we had that material on the linear regression, and we looked at a number of examples, and we have seen that linear regression is so applicable everywhere, starting from very very earthy, very low applications like house prices and well, in general, prices or sizes of the earth things, and ending essentially with the laws the universe works according to, right? And well, so essentially what we do in linear regression is we just take that data set which has well, a number of explanatory variables or a number of features, and we have the dependent variable, and we take a specifically designed algorithm and draw a very, very straight line through that cloud of points which our data represents. And we looked at, of course, just to visualize, we looked at very simple examples of one-dimensional problems where we have one-dimension explanatory variable or a scalar explanatory variable, such as the number of bedrooms in the house or the average number of bedrooms in the house, and our label, or well, our dependent variable is the median house price, right? So, and we have seen that cloud of points, which is nicely elongated, and we were able to design the algorithm which draws a straight line through that cloud of points. But again, the situation generally is a little bit more complicated, and you work with a very well, not necessarily very multi-dimensional, but normally with multi-dimensional data. And you can think of, of a size of lemons from a lemon tree, where a lemon tree is characterized by age, by height, and by latitude, for example, of the garden where the lemon tree is planted, right? So you have three independent variables or three explanatory variables which are trying to explain the size of the lemon, right? And you create a model which, which can be linear, suppose it is linear, right? And we have designed the mathematical machinery to draw a straight line through the cloud of data points, and the data points, each of the data points represents a size of the lemon given the tree age, tree height, and the latitude of the garden, right? And that's already a three-dimensional situation, but you can imagine very multi-dimensional situations where the number of features is like thousands or maybe tens of thousands and so on. And that's what data science currently works with, and that's the big data in general, big data problems. Right. However, what we have done there in the linear regression, we have put a number of assumptions in there, right? Before we derived it. And we have seen that we derive it based on the minimization of residuals. And we literally just took the data set, right, which is normally distributed, or which has a normally distributed error around some sort of a mean value for a particular value of x, right? And we assumed, and this is the core assumption in our derivation, that this error is distributed normally, and then we were able to calculate or to define a minimization problem, right? And we minimized the residuals or the distances between the regression line for a given x value, right, and the measurement at that x value. So the whole task there was to design or to derive the criterion for beta, which is our parameter of the linear fit, right, which is the parameter of our straight line. That minimizes the total error, and we assume that the error is distributed normally, and we used it literally, analytically, we used it and derived the beta and how to calculate it. And we've got a few relatively simple equations on essentially where we substitute the data and get the values for the linear fit, or even better, we have done some sort of filtering problem as well, where we can substitute the or where we can connect the data to the filtered data, and that connection was designed as, again, as a matrix, and that matrix was called hot matrix. So you can look at the details in the previous lecture. So what we will do today is we will try to generalize it. We will try to generalize the linear models to embrace a larger range of different distributions. Again, what we need to remember is that we derived the linear regression based on the assumption of normality of error, which is a very limiting assumption, right? So what we want to do is we want to expand our ability to fit those straight lines, but the trick is they become not straight lines anymore, except that we need to figure out some sort of a mechanism which will convert our straight lines into non-straight lines, right, and back. So we can sort of convert the data that way that somehow differently distributed error becomes normally distributed, and this is done by the data transformation, right? And then we are already in the well-explored field of drawing straight lines, and then we just apply the linear model. And we can also transform the things back if we need to, but yeah. So that's what our today's lecture is. What we need to do is, first of all, we need to define something which will help us to sort out the generalization. And that thing is called exponential family of distributions. And then we will see how, using exponential family distributions, we can design the generalization of the linear model. Now, we have already seen something which is literally doing the space transformation, right? Remember, we were talking about the distribution of the salaries in one of the first lectures, right? And we have seen that there are in linear space, when we plot the linear values of the salaries, right? The salaries are distributed such that that they have a very heavy skew, and there are outliers and so on. But when we take the logarithm of the distribution, everything becomes very, very right and very, very normal, and we literally see the symmetry which normal distribution assumes, and we literally see that it's a nice bell shape. Right, so we had something like this in one of the previous lectures. Although now I'm wondering if it was about the salaries or about the phone bills, something like that. But anyway, you can imagine, right? So we already tried to do something similar. We tried to transform the data that it fits better the distributions we know well and we have studied extensively. Right? So again, what is happening is that linear regression assumes that normally distributed error term, right? And well, we also want that the response variable y is continuous, right? Because I mean, what essentially this is just an equation where we substitute the numbers and we get the numbers out. So that's what we want to do, right? So the things like true, false, or 0, 1, sorry, 1, 0, right? If false is 0 and true is 1, are not really well suited for this equation. Right, and we need to think about something what we can do with the data and with this equation, and essentially we need to think about doing some sort of manipulations with the distributions, right? And the distributions, there are many of those, right? So we have looked at the normal distribution, and this is what we are very much used to. But there are many more other distributions. There is the Poisson distribution, which is integer distribution, which is discrete distribution, which describes the counts, right? There is the binomial distribution, which tells me the proportion of counts yes versus no, right? There is a gamma distribution, which is again a continuous distribution, but which is very different from a normal distribution. And this is, well, this can describe the time we need to wait until the fourth customer arrives to the counter, for example, right? And there is also the beta distribution, which is a general distribution. So there are all those distributions which are already there, which we know about them, right? But we have derived our linear model based on the assumption of normality of distribution of the error, right? And we want to do all those distributions too, right? But we don't want to derive a separate method for each of them. However, what we do is we know that all those distributions have exponents in them, or they can be transformed to have those exponents in them. I'm wondering if I switch the pen on and will be just doing like this, if it helps. right? Maybe just for myself. Okay, so we note that all distributions which are here in the list, and there are many more distributions which also have exponents in them, right? But all those have exponents in them. And this fact can be utilized in a really wise way, which I'm going to show you a little bit later in a few slides. But what I want to talk a little bit more is essentially the transformation and why we need some sort of a generalization. So again, linear regression assumes that normally distributed error term, right? But normality is not everywhere. It doesn't apply everywhere, and we know that there are multiple processes which lead to different distributions. So what we require is that the response variable needs to be continuous. So we still want to have some sort of a number out of it, right? But in principle, we can have a more complicated dependence on my feature vector, sorry, not on my feature vector, but on my data x, right? And we can have, for example, well, yeah, on my feature vector x, if you want, right? So, and we can have something like this, right? So we can have my y, which is dependent on w1x squared, right? Plus w2x plus b. Now, in the x space, you can see, right, this is not linear thing anymore, and this is not a straight line anymore. And this makes the things more complicated, of course, right? Or we can think about even worse scenario where we have logarithm of y, which is equal to wx plus b, right? And this logarithm is, of course, a very different thing from just y, right? So those situations somehow need to be accommodated, right? And taken into account. And we don't want to derive each time a separate model, which is, again, which is time consuming, which is, I mean, after the 10th model, it will be very boring, right? So we want to have, and again, as mathematicians in a way, right? We want to have some sort of a generalization. We want to have some sort of a big technique which embraces all those different possibilities, right? Now, in the first case, we can do a very interesting thing, right? So we can just say that x squared is z1 and x is z2, right? And we've done the job. So effectively what we have done is we introduced, or we, well, engineered a new feature, if you will, right? And we've put it in, and then everything is fine and we can apply a linear model, right? So what we have done here is a very interesting thing. We have taken x and we converted it into something different. We have converted one space into another space. So what we have done is we have transformed one space into another space, and we somehow we like stretched it or twisted it, right? So my data became aligned with a straight line. So a straight line approximation or a linear model can now be applied. Right? Now, for the second case, it's even more interesting, right? What we can do here is we can apply the transformation to y itself. So we can take an exponent of the left and the right-hand side, right? So we can just take the exponent of the whole thing here, right? And then we will have my y, which is sort of linear y, right? We will have the linear function in there, but we still have this exponent, right? And this exponent is what we will be looking at, essentially. This exponent is some sort of a function, right? Now, here I represent it as an inverse function, g minus 1, right? Which converts our nonlinear problem here, right, into a linear problem here. And then again, we can apply our knowledge about how to draw a straight line through the cloud. So what we can do, again, is we can take our data and the space our data is embedded in, right? Transform that space somehow so the error around the mean value becomes normally distributed. And then, after we have done that, we can apply the linear regression as we have done it before. That's the whole trick about the generalized linear models, if you want. Now, how to do it, or how to do it exactly, right, is a completely different business, and it will take a little bit more time. So, as I have already told you, what we have is those distributions which have exponents in them, right? And in principle, they, after some algebraic manipulations, can all be brought in some sort of a common form, which is given here, right? And this form, again, can be transformed into a complete exponent, which is here, right? So I will show you what I mean. I will literally derive it on your screen, and there are all those derivations already uploaded from the last year's lecture, right? So hopefully you will not get lost, and if you have, just drop me an email and I'll try to explain it. Right? So, I mean, there is this common thing across a number of distributions. They have exponents in them, and we will utilize this fact. So, first of all, we design some very, very general form, which is this one, right? And there is a function on y, on my data y, right? Another function on my parameter theta. There is this exponent, right? And the exponent also has two variables or two functions of each of the variables in general, right? So we have a function a of y, which is a function of our data, and we have a function of b of theta, which is a function of our parameter. Now, think about the normal distribution. What we had there is two parameters, right? Like mu and sigma. We can assume that sigma is constant just to get rid of one parameter. And then there will be literally one parameter and data. And we will see that we can represent normal distribution in this form. Okay? Now, what we can do is we can rewrite it slightly. So these functions s and t, right? They can be represented as logarithms. And then after they have been represented as logarithms, they can be put under the exponent sign. And this is what I do here, right? So I say that, okay, that this f of y given the parameter theta is equal to exponent of a of y multiplied by b of theta. This is this part, right? And then there will be product or times exponent of c of theta, right? So we have a function exponent c of theta which is my t, right? So this t goes into c of theta, right? And there will be exponent of d of y, right? And this exponent of d of y is my function s. So this goes into here, right? And this can be, I mean, literally can be done in one line of handwritten derivation. If you need help with that, just drop me an email. I'm not going to spend time on it here. Right, so this is my exponential form of distribution, and I will show you later that, well, let's say most distributions we know about can be brought into that family of distributions, right? But there are some essentially some simplifications or just, you know, just studies around it. We can say that a of y, the function a of y here, is equal to y, right? And my distribution becomes exponent of yb of theta plus c of theta plus d of y, right? And that is called the canonical form of the distribution, right? So this is the canonical form. Now, what we also can do is we can say that theta is equal to b of theta, right? So my function b of theta is just my parameter theta, and then the exponential form will be called as the exponential form which has the natural parameter, right? And we have here natural parameter, and this is my natural parameter theta. So natural in the sense that it doesn't go through the function, but it naturally appears in the form. Right. Now, why exponential? This is because essentially if we have two parameter values, theta 1 and theta 2, we can connect two distributions by an exponent, which is very, very interesting again. So let me just highlight what I mean. Right, so we have two parameters, theta 1 and theta 2. We have the same distribution, suppose, right? Or the same family of distributions with the different parameters. And they can be connected by this exponential factor, right? And if we have the distributions written in the canonical form, the exponential factor becomes even with the natural parameter. The exponential factor becomes even simpler. So this is just multiplied by exponent in power y theta 2 minus theta 1, and that's it. So you see what we are doing here. Essentially, we have two distributions with two different parameters, right? And we say that, okay, that there is a mechanism which converts one into the other, right? And the mechanism is very, very simple. The mechanism is just multiplication by an exponent. And the exponent takes the data and the difference in the parameters, and that's it. Right? So those two distributions, the shapes themselves of the distributions will be different by that exponential factor function, and that's it. So this is why exponential, because they can be connected by the exponential factor. Now, why family is probably a little bit more more speculative in this case, right? I mean, essentially, what we have is let's say we have those n-independent random variables coming from the same distribution form with different or with potentially different parameters theta, right? Then we can create the joint probability density, which will be the product of them, right? And again, product of exponent can be very, very nicely converted to the exponent of the product. And you can see, sorry, exponent of the sum, right? And you can see that there are those terms which are just summed over the data and the parameters. And again, if there are, if it's canonical and with the uh, with the with the natural parameter, right? So there will be just y theta plus those functions, right? So yeah, right. So that's what I have just said, right? So if there is the canonical form, we just sum over the data multiplied by b, and we can get rid of that as well. And if again, if y is the data which is identically distributed, right? So if the distribution is the same, it can be further simplified, right? Because theta becomes the same, and well, and y becomes the identically distributed, right? So all that becomes just the power of n of everything under that sum. Okay, right. So what we need to do essentially is just to go through the examples. And let me connect my iPad and show you that I'm not lying. So I just need to I somehow forgot to do it before lecture, sorry. But we will see in a second that it works really well, and you will see that all those distributions fall into the exponential form. So I need to open the application. And to, I don't know, this internet disruption today morning, it sort of broke the schedule. And yeah, and I'm forgetting to do the important things like preparing. So that's the quick time. And new recording, and there will be iPad Pro. Okay, right, so I'll be able to share it now. Can you confirm you see the iPad screen? And I'm writing the things on it. Can you see that? Great. Okay, great. Fantastic. So what we will do is, again, we will take the normal distribution, right? And we will show that that it belongs to the exponential family of distributions. So let's do the exponential family of distributions first, right? So we have seen this just a few minutes ago. So this is my exponential family in general, right? Okay, so what we have is theta, which is parameters, right? And for normal distribution, theta is equal to mu. We will assume that sigma squared is fixed again for the sake of simplicity, right? Okay, so what we need to do now is we need to bring the exponential, sorry, the normal distribution, which can be written as f given the parameter mu of y, there will be 1 divided by square root of 2 pi sigma squared, and there will be the exponent, right? So this is the exponent I was talking about from the very beginning of the lecture, divided by 2 sigma squared. Right? So this is my normal distribution, right? And I need to bring this into this. Okay. So first of all, what we need to do is to bring everything under the exponent, as we have done before, right? So we just say that this is exponent of logarithm of 1 divided by square root of 2 pi sigma squared, right? Multiplied by the exponent of my minus y minus mu squared divided by 2 sigma squared. Okay? No problem whatsoever. No tricks, no jokes, no nothing, nothing. Right? Then we can just say that since exponent of a multiplied by exponent of b is equal to exponent of a plus b, we can use that and we can say that this is exponent of 1 divided by square root of 2 pi sigma squared minus y minus mu squared divided by 2 sigma squared. Can you see that I'm sort of going better here? Right? So I'm already in the shape of my exponent, except that I need to do a few things under it. Oh, right. Yeah. I forgot the log. Yeah, that's right. Thank you. Yeah, thanks a lot. Okay, so you can see it already, right? Well, we keep doing the things, right? So we keep opening everything as much as we can. So that will be exponent of logarithm of 1 divided by square root of 2 pi sigma squared minus y squared minus 2 mu y plus mu squared divided by 2 sigma squared, right? So I just opened that square. Now I can further open it up, so that will be exponent of what I want to do is I want to twist it a little bit, right? So I'll take this right part and write it in front of, right? So it's the same. So that will be minus y squared divided by 2 sigma squared, right? There will be plus mu y divided by sigma squared, right? Because 2 cancels out and minus goes with this minus and becomes plus, right? Then there will be mu squared divided by 2 sigma squared, and there will be my last logarithm, right? So that will be plus log 1 divided by square root of 2 pi sigma squared, and the bracket is closed, okay? So can you see how close I am already? Right? We have mu y, right, here, and we have the function of y, we have the function of mu, and we have some leftovers, right? which we can always join with a function which we would like to, right? So sorry, I'll need to move it up because I'm running out of space on this page. Okay, right, so I can just a little bit more rewrite it. And I can say that this is exponent of y mu divided by sigma squared, right? Plus, in brackets, minus y squared divided by 2 sigma squared, right? Plus a big bracket, which is, so what's left? Y mu is used. I probably want to have here mu squared, right? Instead, right? And then everything will be all right. So there will be just 1/2 of logarithm of 2 pi sigma. Right, I simplified my logarithm because this is the square root becoming minus 1/2. And then there will be so what's left? There will be the minus y squared divided by 2 sigma squared, right? And I think everything is done at this point, right? So I can just take the big square brackets for your convenience. So what we can do now is we can literally shrink it a little bit, right? And write up what we have, right? So we compare this with this. And from here, we can say that a of y is equal to what? So who was following me? Uh, no. Mu is our parameter. So just look what I will be doing. A of y is equal to y, right? But b of mu is equal to mu divided by sigma squared. Yes, Tim, a of y is equal to y. Yep. Right? And then C and D are, well, I mean, literally straightforward, right? So C of mu is equal to minus mu squared divided by 2 sigma squared, right? And D of y is equal to minus 1/2 of log 2 pi sigma minus y squared divided by 2 sigma squared, right? And we can see that this is literally the same as this, right? With all those plugged in. Okay, so there are more derivations you can find in the lecture folder, right? But I have demonstrated how to do it for the normal distribution. Which last step? You mean you mean this one? So we have a of y multiplied by b of mu, right? No. Wait. So this bit is this one, right? This bit is this one. And then you can see that this is exactly as we require for the exponential distribution, right? So this is sort of, algebraic trickery, which doesn't literally produce anything new. What it does is it just tells you that normal distribution can be brought to some sort of a form. Poisson distribution can be brought to the same sort of a form, right? Binomial distribution can be put to the same sort of a form, and we can forget about different distributions. What we will do is we will literally, from now on, just work with this. So we don't need to care about other algebraically very different forms of the distributions. What we know is that they can be converted into the exponential family form. Jason, is it okay? So you can see what I was doing, right? Okay, good. Right, and again, there is probably a little bit more detailed with d of y. Ah, right. Yeah, sure. So I just took this whole thing, right, and said that, okay, why do I care, right? I can just say that all that thing is d of y. And that's it. See that? Exactly. The whole thing is a function. And there will be always, it's not really a trickery, right? So I'm not, no, but this is the function of y, right? So my d of y is a function of y. So y has to be there in a way, right? I mean, it doesn't really have to be like one in some y in some power, but it has to be there. So this sort of mathematical trickery, it's just to, it doesn't produce, again, that's what I'm saying. It doesn't produce any sort of a new knowledge, right? So it doesn't generate anything. It just says that exponential distribution can be converted by algebraic manipulations into the exponential family form. Okay? Yeah, right. Okay. So just don't be surprised when you see such things. We don't really have time for that, but I saw probably the most amazing example of such a trickery when there was like a list of requirements to functions, and the requirements were very, very, very general, right? In mathematical sense. And then the person said, okay, well, there is this list of requirements, right? But a constant works perfectly with those requirements, and we just substitute constant there. Yeah, so it's something like that. Okay, right. Anyway, so I can stop sharing here, right? And we can go back to the lecture slides. Yeah, right. So this is where we are, right? And I have demonstrated you that the normal distribution can be brought to the exponential family, right? Yeah. Um, and this is what we have got, right? So we've got our normal distribution. I'll probably take the laser pointer here. It will be better. It will not be jumping. So we literally have converted the distribution into those, and note that y here goes without the function, right? And if you remember, if we go back to the canonical form, y goes without a function, so a of y is equal to y, right? It means that the normal distribution, assuming sigma squared is constant, is in the canonical form, right? Well, next we show that the Poisson distribution belongs to exponential family, but I don't want to spend time on handwritten derivation. You can literally try to do it yourself, and I recommend you do that, because it's, you know, it well, sort of keeps you in shape. But again, the story is absolutely same, right? So what we do is we put everything in the exponent, first of all. So literally, we take 1 over y, say that this is the logarithm, or this is exponent of logarithm of 1 over y factorial, right? We take lambda in power y and say that this is the exponent of logarithm of lambda in power y. Exponent is here. Then we just sum it up, convert it, and we get the Poisson distribution in the, again, canonical exponential form, because we have y here without a function, right? And we can see how it looks like, right? Now, okay, so we looked at 2 of them, but you are welcome to derive more, and you can literally, you can do it using the same algorithm. Just put everything under exponent using logarithms, right? And then shuffle what's under exponent until you get the separation, which is like a of y, a separate function, multiplied by b of theta, a separate function, right? Plus c of theta, a separate function, plus d of y, again, which will be a separate function, right? So I hope I have convinced you, right, that many of those distributions can be converted into this form. However, what we can do now, right, is we can just say, okay, we forget about all the distributions we had before, right? We just work with the exponential family and that's it. And we can just take the whole machinery of the stuff we have been doing before and calculate likelihood, log likelihood, score function, information, Fisher information, and so on. But what we will do is we will compute something very, very well, or not maybe not very, very, but much, much more general than what we were doing before, right? When we were taking separate distributions and trying to compute, again, using those algebraic manipulations and so on and so on, and trying to compute what that was, right? So again, we can start with the likelihood. That will be exactly, again, as the distribution function itself, except that the function will be on parameter, right? Given the data y. So again, if we just recall what it looked like before, do I have it? Do I have it somewhere? Yeah, right. So remember that this is the distribution function, right, of the data given the parameter. When we go to the likelihood, this becomes a function of a parameter given the data, right? Again, likelihood is a probability in a sense, right? But again, the things are swapped, right? And the shape is exactly the same, obviously, because essentially what we have done is we just swapped the parameters. We said that y is our data, is a parameter now, and theta is the function argument now, right? So everything else remains the same. But then we can play all the same story we have been playing before, right? So we can take the log likelihood, or we can take the logarithm of this exponent. And you can see how trivially simple the things become, right? So there was this exponent, we took the logarithm, exponent disappeared. That's it. And we've got a of y, b of theta, c of theta, d of y. That's it, right? Now, at this point, we can do a very interesting thing. We can take d of y, right, and sort of push it into that a of y function. We can try doing that algebraically. It can be, again, it can be quite involved, but that's okay, right? What we have in the end, and again, what we have is the sign of proportionality here. What we have in the end is this beauty, right? So we have a linear form of log likelihood. Note that there is a linear form on theta, right? So log likelihood of the exponential distribution, or a distribution of the exponential form, will have this linear dependence on the parameter, right? After we convert it. And also it has some sort of, of a meta maybe link to the linear regression. Again, what you can see is that there is the term with the data, right? The term with the parameter, and some sort of a term with the, what is it called? The intercept, right? So you can see that again, that this is a beautiful linear function and we can play with it. And we know what this function is. Of course, each of those are functions themselves, right? We need to remember about it. But the whole thing is a linear thing. So there is no a squared anywhere or b squared anywhere, right? So this is the linear thing in general. Okay. So what we can do next is we can compute the score function, which will be just the derivative of the log likelihood, right? And again, everything is pretty much trivial, right? We have my log likelihood, which is written in this beautiful linear form, which is a of y, b of theta, c of theta, right? We take the derivative on theta and we get a of y as a constant, right? B dash of theta, which is the derivative of the function of b of theta, plus c derivative of theta, right? And we can use, again, the normal distribution to do that, right? So we can play with it. We can substitute there the normal distribution parameters in the sense of the exponential family, right? And everything becomes quite simple. Right. So what we need, I mean, let's we can do it. We can do it by, but it's okay. I mean, you take a of y, right, which is here, which is y, right. There will be b of mu, which is mu divided by sigma squared, right? So that will be b dash of mu on mu, which will be just 1 over sigma squared, right? And there will be c dash of mu, which is 1 minus mu squared divided by 2 sigma squared. So the derivative will be minus 2 mu divided by sigma squared, or mu divided by sigma squared, right? And this is what we get. We get y minus mu divided by sigma squared. As in the previous, manually and hard-worked result, right? You can see that essentially application of this exponential form distributions is quite a useful thing, right? And then we do the same. We just say that that we will have independent and identically distributed y, which has n data points, and then u is the sum of each of those, right? So u of my data set y is the sum for each of the data points, and that will be n of mean of my data minus mu divided by sigma squared, right? And so again, working the same way with the Poisson distribution, we just take those functions, right? Calculate the derivatives when necessary, substitute them in here, And we will see that u of y for one single data point is y minus lambda divided by lambda, or 1 over lambda minus 1, right? Again, substituting there a data set with n data points, we just sum the score functions, right? And we get the n in the final expression. Okay. So again, I recommend you to do that yourself to keep fit, but there is not really a lot of work. You just need to take the functions, right, from the uh, from the exponential distribution a, b, c, and d, right, and substitute them into the score function expression, which is the derivative of the likelihood, likelihood. Sorry, right. And Fisher information can be done again exactly in the same way, which simplifies a lot the life and so on, right? So the Fisher information is expectation of the first derivative uh, of the score function, right? Now the derivative is taken on the parameter theta, right? But expectation is taken on the data, and we can simplify it, right? So expectation will be taken on a of y, and y is the only, sorry, a of y is the only part where the data is here, right? So b of theta is a constant in the sense of expectation, right? And ultimately, what we get is this expression, which is just the information of for a distribution, right? And note that this information, the Fisher information here, is again is given the parameter, but b and c functions, they don't depend on the data, as it should be, again, because we are talking about theoretical Fisher information, not the value of Fisher information for a particular sample, right? So this will be a function of a distribution, not of a data, right? You can see that. Again, if you need those derived, or if you need help in derivations of those, just let me know. And again, we can apply that to the normal distribution. So what we do, by the way, there is this question to you, right? There is the function b, right? And the function b, so I will do it. There is the pen, right? So the function b of mu is in the normal distribution is equal to mu divided by sigma squared, right? Now, in the expression for Fisher information, we have b2 dashes of mu on mu, of course, squared, right? So now, why is it 0? Do you know why is it 0? That's correct. No. We are not trying to find the minimum or anything. We just take the expression b of mu is equal to mu divided by sigma squared, right? Then the first derivative of that, yes, of course, b dash of mu will be what? So this is mu in power 1, right? So the first derivative, no. The first derivative will be, yeah, that's correct. That will be 1 divided by sigma squared, right? Note that it doesn't have mu inside, right? So the second derivative will be equal to 0, right? Because this is constant with respect to mu, right? And again, if we substitute all those values, so we will substitute c dash, uh, what's that? What c dash? What's c in our case? I'll look in my. So c is minus mu squared divided by 2 sigma squared, right? Oh, everything's gone. Okay, but right. So what you do is you literally just substitute those functions in there, and you get the 1 over sigma squared for a single data point, right? And you need to multiply, because this is additive, you need to multiply it by n data points for n data points of the data set. But what you note here is, again, is that it doesn't depend on the mean, right? And it doesn't depend on the data at all, except for the number of records, right? Which is what we already know from the previous lecture when we calculated it manually, right? So what we see here is that information on mu doesn't have mu in it. It has just the number of data records, or the size of the data set, divided by the sigma squared. That's what we have learned before. So essentially, we are just repeating what we have learned before here, but from the point of view of our generalization to the exponential families, right? And with the Poisson distribution, you do exactly the same, right? So the c dash is equal to -1 c double. So the second derivative of lambda the second derivative of c with respect to lambda is equal to 0. You substitute all that in the formula, and you get 1 over lambda for a single point, right? And given n points, we get n divided by lambda. Try to do it at home. If you get stuck, drop me an email. You know that I'm helping. Okay, right. So we've got all that machinery which sort of joins together different distributions, right? Well, different distributions of some forms. Not all of them are exponential distributions, but most of them indeed are, right? And we've got all that machinery, which is quite interesting, right? And sometimes helpful in the sense of reducing the amount of effort we need to put into some calculation. Okay, right? But there is still nothing new really, isn't it? So let's just do that new thing. Let's go back to the linear regression. For the linear regression, as we have done it, right? And as I have already told you today multiple times, our requirement was that the error, well, I mean, in this case, it's not the error which I'm showing here, right? It's the y, which is the dependent variable. But okay, right. So the dependent variable y is distributed normally around some value of the mean, which is given by x transposed beta, right? And the distribution is sigma squared wide. So the standard deviation here is sigma squared, right? Now, what we have here is, again, is my y, which is my data, which is normally distributed, right? And the expectation of y is equal to some value of mu, right? Now, what I can say, again, remembering what I need to do, right? What I can say is that there is some sort of a function of mu which is equal to my x transpose beta. And for this particular case of normal distribution, my g of mu is equal to mu, right? Which is the identity, so that g is the identity function, and my x transpose beta is indeed an expectation of y, which is equal to mu, right? And my y is indeed distributed normally around some mu value, right? So this is what we already have in the normal distribution. What we have done here is a very, very tiny thing, right? We have introduced some sort of a function, which is g, right? Which is in this, only in this particular case, is the identity function, right? But note that we have some sort of generalization here already, right? So instead of having just mu in here, we already have some function g. And we will call this function g of mu, which is in this particular case only is the identity function. We will call this function the link function, right? So this is my link function g, right? Which is only in the case of linear regression is the identity function. But we have made a very, very important step. We have generalized linear regression. So what we have said is that this is not just mu, right? So this is not just mu. This is some sort of a function of mu. Okay, so what we do is we extend the linear regression, remembering that we have already introduced that function and we sort of played the words around, right? But what we say is that, okay, let my y be taken from some exponential family distribution, right? So it can be normal, it can be Poisson, it can be binomial, it can be beta, it can be all other exponential distributions or distributions which can be brought to the exponential form. And then we say that, okay, we have the expectation of y. We always have that, right? Because we have the data y, which is from an exponential family distribution. So we have the expectation, we have some sort of a mean there, right? But what we say now is that the g of that mu or expectation is equal to x transpose beta. And g is my link function. Now, g is required to be monotonic and differentiable for all this to happen, right? But after we have done this, we can just take our data, transpose it or convert it using the g, and then just apply the linear regression, right? And I'll put it again. So what we have, again, this is the very important step. What we have is y, which is the data, right? Which is somehow distributed. But we know that this somehow is still a little bit limiting. So y is distributed from an exponential family distribution. Okay? What we say then is that, okay, the g, which is the link function, is not an identity function anymore. It's some sort of a function, right? Which takes the expectation of my data, and then we can apply the linear regression, right? So then all this connects my data with the linear regression mechanism, which is x transpose beta, where beta is the parameter, right? So instead of having mu equals to x transposed beta as we had in the linear regression, what we have is a function of expectation, which is equal to x transposed beta, right? And this step is essentially creating the generalized linear model. Okay, so we can play a little bit with it. Again, if we start from the exponential family with canonical form, we can say that the expectation is minus c dash divided by b dash, right? So essentially, the link function links the parameters theta with the linear coefficients beta bold in the linear regression model, right? And this can be used. So again, if we have the data, right, x1y, x2y, xny, instead of using the parameters, we can fit those, right? We use p shared parameters in beta, and we use that relationship before, so we can essentially we can find the beta itself. Okay? Again, given the link function. Now, there is there is an interesting point here, which we all need to remember really, really well. There are many link functions, right? So you can transpose your data one way or another, and essentially you can, you can multiply it by constant, for example, right? After you have transposed, you can multiply it by 1, you can multiply it by 2, you can multiply it by 5, and so on. So what you have is effectively infinitely many link functions, but there is only one unique canonical link function for every distribution, right? So what we have is, again, right, how to tell you here. So if we get back, yeah, I sort of jumped a little bit, but okay. Well, anyway, it doesn't really matter. It doesn't really matter. So what we can do is we can take the canonical form with the natural parameter for the exponential distribution, right? So this is where the a function of y, a of y is equal to y, b of theta is equal to theta. That's it, right? Now, what we have is the expectation of y, which is equal to minus c dash of theta, right? And we can say that my link function then is minus c dash inverse of mu, right? And that will be the canonical link function. Now note that this is uniquely defined through the c dash, right? Through the first derivative of function c. So we can look at example again. So we can take the Poisson distribution, right? B of lambda here is logarithm of lambda. This is already in the canonical form because a of y is equal to y, right? And we can say that the Poisson regression or the generalized linear regression applied to the Poisson distributed data, right, is this, right? What we have done is we have computed the link function, which is the exponent here, right? So what we have is the same linear term xi transposed beta, right, for a given data. And we say that y is distributed as a Poisson distribution of exponent, right? And at this point, we can apply the linear regression. Now, in R, everything is much simpler. So I know there is a lot of stuff here to comprehend, but again, I'm an email and I'm explaining the things. Okay. So there are derivations behind all those steps, and yeah, and we can go through that, right? So in R, everything is, of course, is much simpler, but what you want to do is you want to remember that all those machineries which I have just described, they exist in there, right? So in R, you just use the GLM function, right? So there is GLM. What you do, again, this is assuming that wool break data set, or there are some threads breaking or something like that, right? So, but there is the data. So there is three variables, which is breaks, wool, and tension given, right? What you say is there is the formula where breaks depend on wool and tension. Note that this plus doesn't mean that you sum up wool and tension. It means that you create a two-dimensional generalized linear model where breaks depend on two separate variables of wool and tension, right? So you need to remember that. This is not plus, this is we add the variables to the model, right? So this is breaks of wool and tension, okay? Now, we can then, or we should then specify the family of the distributions, right? And that's the Poisson. We specify the link function, which is the logarithm, and then we specify the data set, right, where it comes from. Okay? So what we do want to note is how the link function here is specified, right? Yes, it's much easier in R indeed. Yeah. Okay. So I know that's a lot, right? But what we need to remember is essentially is, well, a few key points here. So first of all, what we have done today is we said that, okay, that there is a family of distributions which can, or which includes all or nearly all those distributions which we normally use. So it includes normal distribution, Poisson distribution, beta distribution, Bernoulli distribution, and so on, because all those have exponents inside or can be converted appropriately, so it can be brought to some sort of a standard form, right? That standard form itself is helpful, right? Because using that standard form, we don't need to compute various parameters or various things for the distribution, such as log likelihood or the Fisher information or the score function and so on, right? We don't need to do that separately for each of the distribution because we have done it in a general form. What we need is just to substitute those functions A, B, C, and D, calculate their derivatives sometimes, and substitute all those into the one single formula and get the answer out of it, right? What we also have learned is that there is a way to derive the linear model for the exponential family of distributions. However, that linear model becomes a little bit more complex. And instead of just having an expectation as an expectation, in the linear model, right? So where we have mu is equal to x transpose beta. We have a function of mu, a function of expectation, which is equal to that linear term, which essentially generates the linear model. So what we do is we transpose, not transpose, but transform the data somehow so that the distribution becomes a normal distribution. And that is done through a function which we call a link function. Now, what we need to remember is that there are infinitely many link functions. However, there is only one canonical link function for each of the exponential distributions. Right? Again, what we have done is we took a data which is much more complex, which is distributed somehow differently from normal distribution, right? We have done some sort of a mathematical procedure which converts this data into something different. And after we have done that, and this procedure essentially involves application of link function to the data, right? After that, we've been able to apply the linear modeling, which we have derived last week, to the data, and essentially take all the results we had from the linear model from the last week and apply it to a much broader family of distributions for the error or for the value for the expectation. Okay? And finally, we looked at how to do it in R. So essentially, it just involves a use of a function which is GLM, but it also needs us to provide the family of distributions, right, and the link function, and then everything is done sort of automatically. Now. The assignment 2, right? It will require you will see it tonight. It will require you to fit a number of models to the data, right? And GLM is what you use as the second step in there. Also, I want you to pay attention to the practicals, because practicals, there is a very nice practical essentially about the GLMs in this week, I think. So if we think about how breaks depend on wool and tension variables here, there can be some sort of dependency on wool separately. There can be some sort of dependency of tension separately, but there can be also some sort of dependency on wool and tension together in the sense of a functional dependence, because we need to remember that all those are effectively our data, right? And the practical will teach you how to specify those models, the formulas, right, in R, because this is a very, very, very useful thing. So which practicals, that was the last page. Which practicals lectures do we need to answer the second assignment? Okay. Well, in the second assignment, what we will use is generalized linear models and generalized additive models, right? Generalized additive models is what we are going to do over the next, I think, 2 lectures, right? So this is the lecture number 7. There will be lecture number 8 and 9, I think, about the generalized additive models. Lecture number 10 will be about the model selection and overfitting and stuff like that, as far as I remember, right? And lecture 11 will just be an overview, and then we'll wrap it up and go to the exam. Okay. Right. Yeah. Well, I would say so. I would say that it's up to week 9. Yeah. I think. Yeah. Sure. Right. So that's it for the new material for today, right? But we can go to the questions, and we have a few minutes for that. And my kid woke up today to to finish the day, and he apparently woke up not in the right mood. uh, um, yeah. So canonical form. Uh, Canonical form is here. Essentially, canonical form is when we have, instead of a function of data, we have just data y, right? So if this is our general form of the distribution, right? Of the exponential family of distributions. So let me just switch it to the pen, right? If this bit can be represented as y only, not a function of y, but y only, right? Then it can be said that that this distribution is written in canonical form. Is it okay? Right. And well, Fisher information is something which is coming from from Fisherian statistics. It's usually called just information, right? So this is sort of amount of information a variable or a random variable has about the parameter of the distribution we want to fit that data in. Okay, so well, there is the data, right? We can fit a distribution to the data, right? But we want to know how well we can define the parameter of the distribution. Depending on the distribution itself and the data, it carries sort of different amount of information, you know, which describes the the well, it's not the precision. It's not the precision. It's nothing like that. So it's sort of amount of usability of the data to define that particular parameter. Maybe it's this way, right? But you can, again, so you can think, I mean, if you have a feeling about how the word information or what the word information means, right? It's the amount of information on the parameter. Yeah, also possible. So you can just try to YouTube it. But again, so the amount of information carries the amount of information on how well the parameter of the distribution can be defined using that data. So again, in the sense of distribution fitting and maximum likelihood estimate, right? Remember what we do. So we take our data, right? And we try to define the parameter of the distribution given the data. Okay? Assuming the distribution is valid for that particular data. So the amount of information or feature information shows how well we can define that parameter. Okay? Again, there is the practical. I think this is week number 5. Yes, yeah, exactly. Yes, of course. Again, so we can think of the normally distributed data, right? So what we have is 1 over sigma squared, I think, for the Fisher information for single data point, right? And then we remember that for a data set with n data points, that will be n divided by sigma squared. Is it sigma squared? Yeah, exactly. Yeah. So, oops. Let me just, switch to laser pointer. Right. So again, this is for one data point. And for n data points, it's n times larger. Yeah. But again, remember that this is for normal distribution, right? So this is for normal distribution where there is no dependency on the data itself. It can be different. Okay. Yeah. Yep. I mean, you probably can go through the Wikipedia page, but there may be a lot of derivations. I don't know. Okay, do we have more questions? The expectation is just mean. The expectation is expected value. That's it. There is nothing more involved than that. Expected value is is mean. No. Look, I mean, I know the material is quite involved. Yes, and by the way, in the sense of exam, I will be asking, demonstrating the exponential forms from different distributions, right? So you will be given a distribution, and you will need to go through the steps of converting it to exponential form. But the good news, however, is that the exam will be open book. So you again, assuming you have decent level of understanding of where those derivations, the detailed derivations I provide, come from, and you can follow step by step, you will be perfectly fine at the exam. Yeah. So you don't need to memorize what you do, but you need to sort of to orient very well in what is going on, right? So there are like structures, and you want to understand that structure. Do we have more questions? No, but look, that's all right, and you may want to again to try it yourself, right? To try it yourself, to maybe rewatch the lecture, maybe look at the internet, look at a few Wikipedia pages, try to do it yourself, like literally derive it yourself. If get stuck somewhere, drop me an email immediately. Those, uh, yeah, right. Um, we can quickly try. So let me try actually. Going through the quiz. So I stopped sharing this, right? And yeah, thanks for reminding actually. It will take a couple of seconds for me to open it. Um, in the right place. It just I'm not obviously I'm not allowed you to show the marks, right? But I can quickly show you a little bit of statistics, I guess, about how it looks like, and why I'm not worried. Let's say it this way. So you can see my screen now, right? This is the statistics from quiz one, and you can see that essentially that most oh wait yeah, that most have fallen into some, well, between 75 and 100, right? And if I yeah, right. So and the questions, so there are few questions which have been which have been a little tougher than other questions. Now, well, I need to stop sharing here because I literally I'm not allowed to. Okay, okay. So that's how it looks like. Right. So we can, in principle, we can share the screen, right? So this is the question which had the lowest percentage of correct answers. So this is for a continuous random variables. Its probability density function can only take values between 0 and 1, and the answer is false. Are you with me? And the answer is false because the probability density function, or the value of probability density function at a given x, doesn't have the probability interpretation. Yes, it's the integral between two values of probability density function gives you the probability. Now, if you don't understand that, drop me an email, right? So it's just I don't want to spend my time for nothing. I just want to know that there is at least one person who doesn't get this idea, and then I will be able to do the handwritten thing which demonstrates that. Okay. Marisa, can you just drop me an email about that, because I will forget. Just an email, that's it, and I will literally handwrite you about the about why exactly this is well, this answer is well, what it is. Okay. Right, so that was random question 8. I think we had problem with random question 15. Right, so in statistics, a sample is always assumed to be IID, and well, the key word here is always, right? I mean, of course not. I don't know. I don't know why this question has had so many problems. But I mean, it's not always necessarily identical and independent and identically distributed. Not always, no. And we have told about that in the lecture. This is what is useful, but it's not always valid. Because there are, there are things like again, like Markov processes where the current value depends on the previous value. There are more complicated things like current value depends on the history of the things, right? And those are already not identical, not independently distributed at all, like completely, right? We just we don't talk about that explicitly. We don't look at those non-IID examples here. But what we need to remember is that it's an assumption which is useful and which is widely used in statistics, but it's not always like that. Okay. Right. What else can? So which one do you want to look at? It's random questions, right? Okay, I mean we can do 9. I don't know. So, well, yeah. Jason, with that, you want to write me an email. Of course, I cannot tell here, which question you have got wrong, because I'm not allowed to. But if you drop me an email, I will be able to do that. I will be able to tell you personally which question you have got wrong. Of course. And the same applies to everyone. I mean, if you are interested in which question you have got wrong, I'm happy to look at your particular submission. It's just I cannot make it during the lecture, of course, right? Yeah, so this one is sort of what we have, again, what we have been talking about. So this is about the probability itself. I don't think so. I'm not sure about the look. The problem is, again, there are questions which may be repeated because a part of the exam. Of course, we reuse the quizzes as well. However, I rewrite a significant part of that. So it's not even because we reuse the quizzes year to year. It's because it's because within one single trimester I cannot produce such an amount of questions so everyone gets a separate question, right? Or separate 10 questions. It's still, it's still a database with questions which are randomized. Yeah. Right. We can look at, so what's question 14? Interesting. QQ plot. Right. So QQ plot is about the ends, PP plot is about the center. Okay. I don't know. I'm not sure. So maybe people just run one same quiz year after year and everything is fine. I don't know. I don't. So. Right. So that's about QQ plot and PP plot. I like that these questions have been answered like everyone was, like almost everyone was able to do that. Well, this is a little bit tricky question, actually. It's about robustness of the distribution parameters. We don't say explicitly about that, but what we have is, or what we have seen perhaps, is that the higher the moment is, the less robust the estimate is, right? So we have seen where we fit the data, where we fit the distribution to the data, the normal distribution to a data sample. Remember that was 30 records or something like that. We have a relatively small error for mu, for mu estimate, for the mean or for the expectation estimate. But the error grows for the sigma, right? Now, skewness and kurtosis are even higher order momenta compared to the sigma itself. So the higher the order, the larger the error is, and the less robust the estimate for those parameters is. But like 60–70% got it right. What is this one? Have a look at this one. Yeah, well, sort of, and well, relatively simple question. So essentially, what we want to know here, or what we want to think about, is how the data is distributed, right? And we had a very nice question in the message boards, and this is very similar to essentially to this question. The question in the message boards was about the modeling of marks with normal distribution. And we remember that normal distribution is defined on the range from -infinity to +infinity, right? And it has non-zero values on the range from minus infinity to plus infinity, right? But the marks can be distributed only from 0 to 100. So essentially, when we need to choose a distribution, we need to remember that distribution is defined on some range, right? And we need to be careful when we select the distribution so that we nicely fit that range, or we do something, because there are truncated normal distributions where one or both ends are cut, right? And those can be used maybe better perhaps for modeling the marks, for example. Right? What else? 14. 14 is we looked at. 9. 9 we looked at. 4 maybe. Yeah, well, yeah, sure. Censoring is just cutting out the bits and pieces, right? So of course it's a form of missing data. Right. Okay. So if again, if you want to see your incorrect answers, just drop me an email. Okay. And well, I guess I covered the most questions where what's this one? Ah, right. So this is yeah, but I cannot see which answers. So this is current weather, which is very hot, hot, warm, cold, very cold, right? And this is of course ordinal, and this is of course categorical. Categorical is because the well, this is not a number, right? The very hot is not a number, and ordinal is because you can put it in the order from hot to cold or from cold to hot in a meaningful way. Right. So I think we can wrap it up. Again, drop me an email if you have questions. Okay. Sure. Yep. See you next week.